Assalamualaikum warahmatullahi wabarakatuh. My name is Amirul Aiman bin Rohizat. My metric number is CD250051. Okay, today I will present about introduction and recommendation. Introduction, recommendation and conclusion. Okay, first of all, in today era of automation, traditional plant watering methods have been improved using smart technology. To overcome the limitation of manual watering, our group developed a DIY smart water dispenser for plants using an Arduino Uno and a YFS 201 water flow sensor. This system automatically measures and controls volume of water supply to plants, ensuring efficient and consistent irrigation based on basic fluid mechanic principles.
Industrial measurement systems are essential in modern engineering because they allow continuous monitoring and control of physical processes. These systems convert physical parameters like pressure, temperature, and flow into usable signals for operators and control units. In fluid-based applications, flow measurement is especially important due to dynamic nature of fluids. In this project, we use the YFS201, a low-cost turbine flow sensor that converts fluid motion into electrical pulses. By integrating a microcontroller and a buzzer alarm, the system not only measures flow in real time but also provides alerts when preset limits are exceeded, improving safety and reliability. Flow rate measurement plays a crucial role in water management, especially in irrigation and plant maintenance. Accurate control of water discharge helps prevent overwatering, which wastes water and damages roots, as well as underwatering, which allows plant growth. In automated irrigation systems, using a flow sensor allows the system to measure the actual volume of water supplied rather than relying only on time, which can be inaccurate due to pressure changes. Additionally, integrating a buzzer alarm that activates when the flow rate exceeds a set limit improves safety and reliability. It alerts users to possible issues such as leaks or pump malfunctions, enabling quick action. In this project, we apply the concept of volumetric flow rate, which measures how much water passes through a system per unit time. Using the YFS201 flow sensor, water flow is detected as pulses which the Arduino converts into flow rate using a calibration constant. We also apply the continuity equation, ensuring consistent flow by using equal tube diameters and minimizing turbulence. Additionally, a buzzer provides real-time alerts based on preset flow conditions, demonstrating simple open-loop control. Overall, the system shows how fluid mechanics principles can be effectively integrated with embedded electronics to create a functional and user-friendly smart irrigation solution.
Assalamualaikum warahmatullahi wabarakatuh. My name is Amirul Iman and my matrix number is CD240126. So now I will explain about our system development and description. So the first part is system overview and block diagram. Okay, this system is an Arduino-based water flow measurement system designed for industrial process control and smart irrigation application. The main function of the system is to measure the real-time water flow rate using a water flow sensor and to provide monitoring and alert function. The system continuously measure the flow rate of water and display the value on an LCD screen for easy monitoring. A buzzer is also integrated into the system as an alert mechanism. When the flow rate exceeds the preset limit of 2 liters per minute, the buzzer will automatically turn on to indicate a high flow condition. This system was first simulated using Tinkercad to verify its functionality and later implemented using real hardware to validate its practical performance. Alright, next for the sensor analysis, our system used the YFS201 water flow sensor. This sensor was selected because it is simple, reliable, low cost, and suitable for low to medium flow rate application. The YFS201 works by converting the physical flow of water into a digital electrical signal. When water flows through the sensor, an internal rotor spin and generate pulse signal. The frequency of the pulse is directly proportional to the flow rate. Since the sensor produces a digital output, complex signal conditioning circuits are not required. Understanding the operation and characteristic of the YFS201 sensor is important to ensure the accurate measurement and proper integration with the Arduino system. Next, I will explain the signal processing and operation of the Arduino. The Arduino Uno R3 acts as the main signal acquisition and processing unit in the system. It receives the digital pulse signal from the YFS201 flow sensor through an interrupt enable pin. This allows accurate pulse counting even at varying flow rates. The Arduino counts the number of poles over a fixed time interval and convert them into flow rate values in liter per minute using a predefined calibration factor. There are two operating conditions programmed into the system. Under normal condition, when the flow rate is below 2 liter per minute, the buzzer remains off. However, when the flow rate exceeds 2 liter per minute, the system detects a high flow condition and activate the buzzer to provide an audible warning. At the same time, the Arduino updates the LCD display to show the real-time flow rate continuously. So as we can see, this slide shows the Arduino coding used in the system. Alright, next. Before implementing the system in real hardware, the circuit and logic were tested using Tinkercad simulation. The simulation was used to verify correct wiring connection between the Arduino, flow sensor, LCD, and buzzer. It also helped confirm proper pulse counting from the sensor and accurate flow rate calculation. In addition, the simulation validates the LCD display functionality and ensure that the buzzer activation logic work correctly when the flow rate exceeds the set limit. The simulation stage help minimize error and ensure that the system function correctly before moving to real hardware implementation. After successful simulation, the system was implemented using real hardware. A water pump was used to circulate water through the YFS201 flow sensor to enable a real-time flow measurement. The sensor output was connected to the Arduino Uno, which processes the signal and calculates the flow rate. The measured flow rate is displayed on LCD screen for easy monitoring. To prevent electrical interference, the water pump was powered separately using a 9-volt battery, while the Arduino system used its own power supply. The LCD and buzzer were mounted in visible and audible position to ensure clear display and effective alert indication during operation. And finally, I will explain the calibration method and process used in the project. Calibration is important to improve measurement accuracy and ensure reliable system performance. In this project, calibration was performed by comparing the sensor pulse output with a known value volume of water. A calibration factor of 7.5 was used to convert the pulse frequency from the YFS201 sensor into flow rate values in liter per minute. By applying this calibration factor, the system is able to provide more consistent and accurate flow measurement, making it suitable for practical industrial and irrigation application. So for the next slide, we will show you our project demonstration. Thank you. Alright, Assalamualaikum and a very good day. Today, we will be presenting our group project titled Water Flow Measurement. For this project, we are using the following components, which is 9-volt battery, DC water pump, PVC tube, water flow sensor, water container, project box, Arduino Uno, LCD display, and lastly buzzer. We have connected the system to a laptop that have been preloaded with the necessary code to power and operate our Arduino Uno. So now we will proceed with our experiment. Alright, so for our project, the buzzer will only activate after the flow rate reach 2 liters per minute. So that's it from us. Thank you.
Good evening and hi, my name is Amos and my matrix number is CD240121. So based on the result, what we have here is we done 6 tests. We measured each test with the measured pulses and we calculated the flow rate and we observed the buzzer status. So during the test 1, the measured pulse is 9.5, the calculated flow rate is 1.27, where the buzzer status is off. In test 2, the measured pulse is 12.8, the calculated flow rate is 1.71, and the buzzer is still off. In test 3, the measured pulse is 14.9, where the calculated flow rate is 1.99, and the buzzer is still remain off. During the test 4 is the measured pulse is 15.6 and the calculated flow rate is 2.08 and the buzzer is now on. At test 5, the measured pulse is 18.4, the calculated flow rate is 2.45 and the buzzer is now on. At test 6, the measured pulse is 21.7, the calculated flow rate is 2.89, the buzzer status is still remain on. So based on the result, what we have observed is that when the flow rate was below 2 liters per minute, the system operated under normal condition. The LCD displayed the real-time flow rate value and the buzzer remained off, indicating that the flow rate was within safe operating range. Once the flow rate exceeded 2 liters per minute, the Arduino detected a high flow condition. Based on the program threshold, the buzzer was immediately activated, providing an audible alert to indicate excessive flow. At the same time, the LCD continued to display the updated flow rate value, confirming the correct system response. So what can you see here is the graph. So as the measured pulse increase, the flow rate is also increased. So during the discussion, what we have discussed is that the main challenges of this experiment are low measurement accuracy, unstable readings, and sensitivity to flow conditions such as turbulence, air bubbles, vibration, and temperature changes. This issue occurred because the YFS201 sensor relies mechanical rotation and an approximate calibration factor, which may not match with real experimental condition. For future project, the experiment can be improved by performing a proper calibration using known volumes of water, installing straight pipes to ensure smooth flow, applying software filtering to reduce noise, adding temperature compensation, and using higher quality sensor when better accuracy is required. This discussion also highlights the instrumentation is very important in measurement as the choice, installation, calibration, and maintenance of instruments directly affect the reliability and validity of experimental result. Proper instrumentation ensures accurate, consistent, and trustworthy data, which is essential for sound analysis and engineering decisions. That's all from me. Thank you very much.
Assalamualaikum. Okay, now I will explain about recommendation. Okay, to improve system performance, the water flow sensor is calibrated under actual operating conditions to exchange accuracy and reliability. Okay, closed loop control is implemented using a relay or solenoid valve for automatic pump operation based on flow or volume. After that, flow stability is improved by editing straight pipe section or flow straightness before and after the sensor. Software filtering is applied to reduce signal noise and ensure consistent data output. Additional sensors such as temperature and pressure can be integrated for more comprehensive monitoring. Data logging and communication feature enable remote monitor and analysis. Finally, system robustness and safety are enhanced to protective enclosure, proper electrical isolation, and regulated power supplies. In conclusion, this project successfully developed an Arduino-based water flow monitoring and control system for industrial application. The system was able to accurately measure flow rate and total water volume in real time using the YFS 201 water flow sensor and Arduino Uno. Experimental results show good agreement between theoretical and measured value within acceptable engineering limits. Overall, the project achieves its objective and provides a strong foundation for future improvements such as closed loop control and additional sensor integration. Thank you.